Welcome to the computer graphics practice video, and the task is Lindenmayer Tree, and this is the C++ video. In this task we'll be implementing a Lindenmayer system or a L system, and these systems are often used to create all sorts of different plants, trees, stuff, patterns. So I recommend you to check out Lindenmayer's book, The Algorithmic Beauty of Plants. So lots of plants here. Here he describes like some background and the motivation and all sorts of different patterns you can kind of do with formal grammar systems. Again, patterns and you can read like how to define sorts of different systems like this zero context L systems, bracketed L systems, and so on. What are the differences? Stochastic L systems, what can you generate with those things, how, and there's like also a whole lot of information about different patterns in nature, how to generate those mathematically, some pretty cool visuals, algorithms, and so on. So I think it's an interesting read for everyone interested in patterns and nature and math. So feel free to check this out. Okay, but here we'll be implementing this stochastic zero context L system with those rules, or you can come up with your own rules as well. And then you should get some picture that's similar to this. Okay, but let's take a look at the code. So this is the base code, and if you initially run this, what happens? Okay, so there is some bug in the code. I think this print is in include stdio.h. Okay, and now you should get this white screen, and in the console there should be this string printed out. Probably add this line in the base code as well. Now what's going on here is that we have Allegro back, so this is a 2D task. There are functions iterate system, so with L systems, because these are parallel rewriting systems, we want to rewrite or use the rules on the whole word at once and do this multiple times in a row. So the first iteration, we start from the initial axiom, we use some rules on it, we create a bigger word, then we use some rules on each letter of that word, create a bigger word, and so on. So this is what this iterate system does. Rewrite system does one rewrite of the entire system, and replace all parameters. So we'll be using some parameters. If you look at the description here, then this A needs to be able to rotate by some angle A. So this is what substitutes that. And draw system draws the final string as a tree. We have a struct of rules, so each rule has a probability and has a value. So this value is kind of the right hand side of the rule. And we also have a map of rules, so these hold for each character a vector of different rules, meaning that you can assign many rules that have the same left hand side, but their probabilities are less than 1, and they have different right hand sides. It's also a vector of generated systems, a random number generator, so a real number uniform distribution from 0 to 1, and yeah, so this is just something to create a float out of a string. So I don't know, on Windows this has problems. This function in Linux, it's in the standard library, but on Windows for some reason it's not. Here we initialize the rules. So currently there is only like one rule which says that with 100% probability we substitute A with this string. So this is why when we run this, we get this value here. And we actually have it twice, as you can see. Okay, so init systems. So as you can see, we iterate the system 2 times. If we put 1 here and recompile, then we will see this 1 time. So the second iteration overwrote this last A and added the second repetition of that rule. And when you have implemented everything, then you can probably uncomment those lines, and those should generate you a picture similar to the picture in the task description. Yeah, so when you press space, it clears the systems and creates new ones. Iterate system, so this is the iteration, so we call the read-write system on the state as many times as there are iterations. And read-write system, so this is what rewrites the system, replaces the rules, takes each letter, sees if there's a rule to substitute this letter with something else, and does that. Okay, we'll come back to this quite soon. Now this is the place that replaces everything that is in the form bracket a bracket with something where there should be a bracket, then a float value and another bracket. So this float value should represent the rotation. This is the part and instructions that should help you create those random angles for each of the branch. Okay, but let's move down. So here's the main loop. This just draws all the systems in the systems array or systems vector that we had at the screen on a grid. But important things are down here. So we have a turtle. So what is a turtle? So there is this notion of turtle graphics. I don't know where it comes from, but you have a turtle, and this turtle has a pen. So I don't know, maybe he's holding the pen or something, and this turtle can move. It can move forward. It can also turn right, maybe at some angle, then move again, turn at some other angle, and so on. It can also, in our case, revert back to some previous state. For example, it can go back to this location, do a different rotation, and move that way. Maybe come back again to the same location, do a different rotation, and move this way. And then again rotate, move, and so on. And this is the logic that kind of helps us draw those trees. We have this turtle or a pen that can draw a line, turn, draw, and move back to the previous states, and so on, and draw those hierarchical structures. You have, this is probably taught in some initial programming course. So our turtle has this position, so where is our pen right now? It has a direction, where it's facing. It has this line thickness and length. And we initialize it with some values. Okay, and in the draw system function, we'll be actually using this turtle to draw our state of the system at some position. So the first thing we want to do is, depending on each letter in the state, it should do different things. For example, with F, it should just draw this segment. With plus, it should rotate by the amount specified after this plus sign in brackets. With minus, it should rotate the other way. And those brackets will save and load the turtle state in a stack. But we want to implement this F initially. So this F, and you can also read about this in the task description, it should draw this line forward, which represents one segment of a branch or a trunk. So for this, we need to use the Allegro draw line, and we also need to move our turtle forward. So let's go see this Allegro draw line from the manual. and let's see what parameters it wants. So x1, y1, x2, y2, color and thickness. So that's great. This is what we need. Okay. Now the color, we actually have this color defined as this global variable that gets a value in the event loop. But anyway, it's a global value, so we can just use that. Now the thickness, so that's the turtle's thickness in the turtle. So we take the thickness, and that's the thickness. Now x1, y1, x2, y2. Now those should be like the position, the initial position of the turtle, and the position after it has moved. So you can see that set the position 2 values based on the current turtle's position, length, and direction. So we need have this position 2, and we need to basically say that it is its x coordinate is turtle position x coordinate plus the turtle length, so how long the line should be, times the turtle direction at x coordinate. So how much actually moves in x, or like is it rotated, how is it rotated, that specifies how much the x coordinate changes. And the same thing we do with position 2 y coordinate. So we take the turtle's current y coordinate and we move it depending on the length and direction vector inside the turtle struct. Now we have x1 and y1, so those are the turtle's initial positions, so x and y, and we have the end positions, which is the position 2, 0, and position 2, 1. And after we have moved, we also want to assign the turtle's new position. I'm going to do it like this, as position 2 x coordinate and y coordinate. Now there's one more thing you should do here. It's that we should multiply the turtle's line length by this value and thickness by that value. So that makes the lines kind of be a bit shorter and a bit thinner each time we draw sequential branch segment. So maybe we'll do it after this line. So turtle length, we multiply it with 0.98, and turtle thickness, we multiply it by 0.92 float. And this should be cool. So let's see what happens. And currently we get this line on the result. And well, currently the result is this. And this is okay. So we can notice that there are 2 f's in the string, and but it's currently perhaps difficult to say, is it 1f or 2f? So what we can do is we can go to the rules part, and when we have specified this rule, so let's just specify 1f to see is it that, and we can see that 1f is shorter, and I can also specify like 3f's there if I want, and I can see that now we have 3 times this f line drawn. And I also want to test if I draw more f's, then yeah, the line actually is getting like thinner towards the end there. Although it has like this pixel value precision, which isn't all that pretty here. But I think it's fine for now. The next thing we want to do is, let me put this previous rule back up here. We want to be able to rotate the turtle. So this currently should breed the angle, but the parameter replace that's here. This is something that you can do yourself. Currently we are just going to say that this angle is always something like 20 degrees, and we also want to make it to radians, so 20 degrees radians. And in like the case of a minus, let's say it's minus 20. Now, there's also one important thing, so plus and minus, and in the task description you can read that plus is supposed to rotate to left and the minus is supposed to rotate right. So this left is probably like counterclockwise and right is clockwise. So this is something we also have to keep in mind here. And now the question is how to rotate the turtle's direction based on the angle. And this is something that we have done many times in this course. So one thing how we can derive this is, you remember there is this rotation matrix, right? So cosine of alpha, sine of alpha, minus sine of alpha, and cosine of alpha. And this can rotate any vector x, y by just matrix vector multiplication. Now, what does this say is that the rotated x is cosine of alpha times x plus, actually it's not plus, it's minus sine of alpha times y. And the rotated y is sine of alpha times x plus cosine alpha times y. So just remembering this matrix, you can write out how to find new coordinates of a vector that should be now rotated. Now one thing you need to keep in mind here is that in order to find the rotated y, you need to know the initial x. So you can't use this last x, the x you just found by rotating the vector, because of this you can't just directly assign this rotated value to the vector we are rotating. We have to use the previous initial value of the vector also in order to find the other coordinate. You'll see what I mean by this in code as well. So now we want to rotate our turtle direction, and we need to have another value. Let's say x is turtle direction x, and what did we write? We multiply this by the cosine of the angle, and we subtract from this the turtle direction y, and we multiply this by the sine of the angle. And we also find the y, which is now x coordinate multiplied by the sine of the angle plus the y coordinate multiplied by the cosine of the angle. And I can just write like something like this here, because this turtle direction 0 is also used in finding the other rotated coordinate, so I need separate variables. And now when we have rotated it, we can say that turtle direction x is new x and y is this new rotated y. And we want to do the same thing up here as well. Okay, and let's see if this made any change, and it did. Now we have this rotation to the right, which might not be correct. So if we look at the description, plus should rotate to left, but currently we have rotated right, although there's a plus here. So in that sense, we want to make sure that the angles are different here. Okay, now we have rotation to the left, hopefully here. Of course, in the final submission, you should fetch this angle from the string and have like this angle that you read used as the angle of rotation. And maybe this minus is in the wrong place in that case as well, so make sure to check that out. Now this draw system function has two more symbols it needs to do something with. When we have this square bracket, we should save the current turtle's state. So this means that the current turtle that we have here we want to push to this turtle stack. And this means that we save its state, and when we get another bracket, then we load the last saved state from the stack using pop. So this is pretty much what we had done before with the matrix stack. Currently, now we have a turtle stack. And when we save this turtle to the stack and start the new branch, then this Mr. Leonardo guy has rumoredly determined that the child branch should have the 0.707% kind of the weight of the parent. So we need to change the thickness accordingly. Up here we are changing the thickness by a very small amount, just because like the newer segments should become less thick or thinner, but here when we have a branching, then they need to be even more thinner than the main branch. So don't forget about this. But one more thing we're going to do in this video is that if we now have multiple rules, so let's say we have 3 rules, and maybe this first one rotates one way, this rotates the other way, and let's say that this last one doesn't rotate at all. It just goes forward and creates another branch. And let's say that the probabilities of those rules are maybe like 20, say 40, so that's 60 and another 40. So it's more probable to turn this way or go forward than to turn that way. But if I currently run this, I still get like only this result because our rewrite system function just takes the first value. And the question here is how to pick a value from the possible rules, so those according to the probability. This is an interesting problem in the sense that if you haven't had this problem before, then the solution might be quite interesting. If you have, let's erase this thing. If you have 3 things, let's say A, which has a probability of, what did it write here, 20% of being picked, then we have B that has a probability of 40% of being picked, and C also 40% of being picked, then how do you determine which one was picked? What is the code for this? And well, what you can do is you can have some kind of a random variable. So from some, let's say from 0 to 1 distribution. And now the question is, okay, so what do you do with this random variable such that you can now pick one of those values? And this is something that you should try to think about. So one thing we can see that if this value was below 0.2, then we probably want to pick A because it was 20%, right? But what if it was above 0.2? Then how do we determine which one of those is picked? And the solution is, let's have another value, and let's call this, for example, something like running probability, or I don't know, or maybe the current probability, whatever. This is initially something like 0, and when we want to consider case, should we pick A, we add to this the A's probability. So that would be 0.2, and we're considering A. And now we compare our dice roll probability that we did once with this 0.2. If it was below this, then we take A, we're done. If it's above this, then the next step is to add the next element's probability to this running probability. And that would give us 0.6 to consider B. And now we can see that was this probability less than 0.6. We know it wasn't less than 0.2 because otherwise we would have picked A. But if we now check was it less than 0.6, then it needed to have been between 0.2 and 0.6, which is 40%, which is exactly the probability of picking B. So if it was, then we pick B. And if it wasn't, then we again add another 40% to get 1, and most probably we pick C then, because our value couldn't be larger than 1. So this is how this choice of an item, where each item has a different probability, is usually done. And this is exactly what we want to do here, because each of the rules has their own probability, right? In this rewrite system, you should do that. So first thing we need is this probability. How to get a probability? And we had this, how to get a random value. We had this generator and a distribution. So we sampled from the distribution via the generator, and it gives us a random number from that range. So something like this, and we assign it to this probability value. So our dice roll probability is that. So that is from 0 to 1 range. Okay, and now we want to create a loop over the rules. So something like, let's not use I, let's use J. And now we need to know how many rules there were. Let's even perhaps use this rule here to assign the possible rules into. So these are the rules with the same left side now, where the character of the left side is the same character that is currently in question. And it may have several rules with this left side, so we ask for the size, and we J needs to be less than this, and we increase J if we need to. Okay, another thing we need to do is have this running probability, and we need to make it 0, because otherwise it might be something else from the previous iteration, and then we get the wrong result. And now we're going to add to the running probability the rule at the J value and probability. So this is the current rule we're looking at. So is it A, B, or C? And we add the probability of that rule to the running probability. And now if our probability, the dice roll we had, was less than the running probability, then we know that this is the rule we want, and we can assign to value the current rule. So like value assign and the rule at the J, so this is the rule that we watched or checked currently, and its value, which is the string value we need to use to replace the current char value. Okay, and one thing we also need to check. So initially this value that's appended to the new state, it gets the first rule that's possible. So that's, I think it's fine. We could take the last rule. The problem might be that if we have written some probabilities to the rules like 0.33 and then roll 0.991, then no rule would get assigned to in this loop. And in that case, we want some default value to be assigned. One more thing we have forgotten here is we need to, of course, stop this loop when we have assigned a value. So otherwise we would always assign the last value, and that would be wrong. Okay, and let's see what this does. So this is of course a semicolon, and yeah, so currently I have gotten again this, but no idea if this is right or not. So we probably now need to make several different systems and see if those vary enough, because in C++ the random values are kind of determined. So what I got is now this result, which and with these systems, and this maybe kind of looks okay. So what do the rules say? The rules said that 20% probability that we turn plus was left, right? So let's recheck this. Yeah, so plus is left. 20% chance that we turn left, 40% chance we turn right, and 40 that we keep moving forward. And it seems like many of those are turning right or moving forward, and a bit less of them are turning left. So for example, this is left, 2 left, 3 left, 4, 5 out of those 25. So it could be something like this. So 5 out of 25 is 20%. So it's pretty much the result we would expect. Okay, and then this is pretty much all that we are going to do in this video. Now, what else do you need to do is to finish this parameter replacing. So you should find some random values for the rotation, and in the end there is this saving of the state and popping the state. So branching should also be implemented, and this decrease of white in the branches. And when those two things are done, then feel free to come up with some interesting rules here, or just use the one mentioned here. So this is a sure way to generate this kind of a picture, and you can check is it right or not. But if you're interested, you can come up with your own rule set. And this is pretty much it for this task. I hope it's interesting, and I hope you create some cool looking systems and trees, and have fun.